Hello everyone and welcome to our first webinar of 2025. So today Mark and I are going to talk through combining underwater sonar data with mobile laser scanning data for some topographic survey outputs. So introduction to the speakers, myself and Mark. So Mark's going to be the main person speaking about the sonar stuff today. He is our specialist at Global Survey in this, and if you have any questions on the equipment, you can ask him about it afterwards. We will now be going on to the combination of the data. If you have any questions and answers, as usual, please can you leave them in the questions tab, and we'll have a Q&A session at the end. So when we're going through this combination of sonar and mobile laser scanning data, there's kind of three things to this. So the first thing we're going to do is discuss a bit of a background to this capture. Why did we do it? What was the purpose of getting all this information? Secondly, we're going to go through the field capture workflows. We're going to look at what technology was used, a bit about those workflows and how it was done in Whanganui. And then we're going to conclude with a 3DR software workflow to show you how to generate the contour maps and heat maps of the elevation changes on the bed and look at combining this with the point cloud information. So we did get quite a lot of data for this day. Mark was the one who was out capturing it all on site. You can see here we've got some of the point cloud over that contour lines and heat map. So why was this data needed? So over to you, Mark.
Okay, thanks, Kirsty, and welcome everybody. So I guess the million-dollar question is, why was this job done? Well, if you can see on the right-hand side of the aerial image, we have a ferry location, and that is the Q West boat manufacturer, and they are building new electric ferries for Auckland Harbour. And once those ferries are in a state of being able to float, they need to get the ferries around to the main Whanganui Wharf area to be able to finish them off. The main problem was there was not enough water to be able to float them around to the Whanganui Wharf. So that was a primary problem. And then the other problem is effectively from the boat ramp out to the ocean. It was very difficult for recreational users to get back and forth. It was very, very tide dependent. And so if somebody was out at sea and the weather cut up, they could struggle to get back to the boat ramp unless they hit the tides correctly. So like all of these problems, it's had a huge build-up of material coming down the Whanganui River for many years, which has just silted the whole area up. A port company a few years ago purchased an old dredging solution from the South Island, and they did attempt to do some of this dredging work themselves, but due to the type of material that had built up on the bottom, this did lead to a lot of problems. So one of the goals of the capture was to really be able to readily identify the areas and the material that they were looking to pull out, and then bring in purpose-built dredges, amphibious dredges, to be able to readily navigate both through low tide and high tide, and remove this material once and for all.
So the second reason for this capture was that we wanted to get some of the surrounding topographic features in the area. There's a shipwreck at the end of a sandbank, and then there's this quite old wharf, and then obviously the sandbank itself. So getting some more information on this was very important. So we wanted to first get that waterbed map and then get some of the surrounding topographic features in the area. So what do we use and how do we capture this information to create these outputs? Well, Mark was on site with the client. He had a CHCNAV RS10 and an Apache USV. It took about 1 day on site, which included about 6 hours of using the Apache Sonar device. We've got little stars next to this because that should have taken a little bit less, but due to some training time involved there, it was a little bit longer. And then there was also about 2 hours of capture with the RS10. So for the RS10, only some select kind of features were picked, but if you wanted to get some more information, you could spend a little bit longer walking around the wharf doing that as well. So about a day's capture overall. So these are the two devices that we used. On the left, we have the Apache 3 Pro USB, and on the right, the RS10 mobile laser scanner. So back to you, Mark, to go through a bit about the Apache Sonar device.
Okay, the Apache 3 Pro is a fully integrated unit, and so it has a 4G modem, so it operates like a GNSS rover and connects either into your UHF base station on site or into our SmartFix service. It's got a built-in single beam echo sounder and a dual GNSS RTK system. So the stern antenna provides our GNSS fix, and the antenna mounted on the bow provides us with heading information. So you'll always get to see the direction that the vessel is pointing at, even when it's very difficult to see it 500 or 600 meters away. So what we're showing here is the vessel traveling underneath the bridge, and of course we are immediately losing GPS signals underneath the bridge, but the fully integrated IMU is working in conjunction with the GNSS, and it will provide us with a robust position underneath the bridge in order for us to carry out straight line mapping. So here you'll see it from the viewpoint of the operator, and the vessel is heading towards waypoint number 1, and it's now started its recording of its bottom position, and of course it's predominantly using GNSS fix out in the open. And as you then go underneath the bridge, you will completely lose track of the majority of your satellites, and it will then the IMU will kick in and keep the vessel on a straight line path towards waypoint number 2. So along with the another function of the IMU is how much the vessel is actually tilted in the water, and once again the GNSS and IMU combine, and you can see the sounder is effectively recording forward of the vessel at this stage, but we will post-process this, and it will correct the attitude of the position or the attitude of the sounder and the position combined to give us a more accurate result. So here's an example of the before attitude correction. And so you can see lots of hilltops and so forth, and the data is actually quite messy. And then it's a very simple process in the software to create this and give you a nice smooth result after the attitude correction. Okay, so another built-in feature is the obstacle avoidance. So effectively, it has a radar on the front of the Apache 3, and so if you're coming up to a pylon or a wharf structure, then the radar will pick this up approximately 10 meters, I should say, in ahead, and it will automatically look to move around that vessel, around that obstruction. Okay, and here's an example of the obstacle avoidance. So it's picking up the pylon in the water, and it's just going to record information offline, go around the pylon, and then come back online. If you want to get more data in and around the pylon, then you can simply take it out of automatic mode and put the vessel into manual mode and just drive it very carefully in and around the pylon and collect data at the same time. Okay, one of the other features of the vessel is it's nice and portable. So as you can see there, it fits in the back of a small SUV, small vehicle, easily enough, and it is small enough and light enough for one person to carry it. I would suggest, for health and safety reasons, that you look to carry the batteries separately, because they do add considerable weight if you are picking it up yourself. Software is very intuitive, very easy to use. The system comes with a 10-inch Android tablet with built-in communications, built-in software for the data collection process and the processing software. So anybody that's used a drone will find that this is very similar, very similar setup as far as run lines, etc. is concerned. Here we are showing the 10-inch tablet with the 2.4 gigahertz radio solution out the top. It's a little bit difficult to see, but the real-time camera view is in the bottom right-hand side of the screen. So here's an example of the collected data, and all color binned. So the darker the color, the shallower the water. So at the bottom you'll see a fairly decent channel that is marked in blue already, but in around the wharf, and especially in around Q West, very shallow waters. So this is the post-processing software inside the Android tablet. Effectively, we can run ourselves through each of the individual recorded lines, and if there are any spikes or noise in the data, it's very easy to clean that noise out. And then you effectively, if you hit the 3 corrections tab or attitude correction tab at the bottom, it will take out it will correct for the attitude correction, and then you can move on to actually sampling the data that you've collected. So there's a few different ways of launching. Obviously, if you can walk into the water, then just launch it straight off the beach. In our particular case, we did a little bit of that directly from the boat ramp, and we also launched directly off the wharf using some strops, and then there was a ladder down to the water to be able to release the strops and to take control of the vessel that way. But I have been assured that you can throw the boat into the water from up to a 3-meter height, and even if the boat lands upside down, it will self-right, and you'll be good to go from there.
Awesome. So that brings us on to the second device we use to capture that surrounding information. So that's the RS10 mobile laser scanner. So the RS10 is a SLAM device. If you don't know what that is, don't worry, we'll come on to that in a second. This device is so that you can capture in a continuous scan. We had the 16-line LiDAR, which Mark was using on site. So this gives about a relative accuracy of 1 centimeter. But what is quite important about this one is that it also has a GNSS receiver inside it. So this means we can get the data, or the point cloud data, in the same coordinate system as the sonar data, which helps with combining it together. There's an absolute accuracy here, which is saying 5 centimeters, but you can post-process this down using the Rhinex files from your local base station if you're within 15 kilometers of a SmartFix location or of your own base. So SLAM stands for simultaneous localization and mapping. You probably hear the term quite a lot if you're doing a lot of laser scanning stuff, because it's all the rage at the moment. That's because it's letting you go from the workflow on the left with static laser scanners to doing one continuous scan or walk to combine all the data in one go. And the idea with SLAM is that you're constantly walking around and it's capturing measurements of the environment around you so that it can localize where you are in a space whilst mapping the surroundings. So this is a data set from Papa Toi Toi car park. And you can just see kind of the trajectory line there of the walk. So what's quite good about the GNSS part of the RS10 for this data collection is that that GNSS connection means that you can use the location to control the movement through that environment. So when you're taking all the measurements with a SLAM sensor, it's constantly basically doing loads of maths. It's capturing points on static features like walls or whatever landmarks are kind of around as you move to constantly calculate where you're actually going. It's, yeah, essentially a load of maths. I won't pretend to understand the full extent of this formula, but the idea is that you have a position, and as you move along, it's capturing landmarks and using those same features to constantly figure out where you're going. And it developed in robotics for the movement of autonomous vehicles. So one of the problems in the past, when these sensors, one of the problems when this algorithm originally came out was being able to capture static features and constantly be able to do that mapping. So if you were to capture, say, a moving object, that would be problematic because it would affect the maths and you would potentially get a little bit of slip. But over the last few years, these algorithms have become really strong. And I think what's really testament to one of these is the use of this in forestry environments. So there's been quite a lot of forestry managers that go out with SLAM scanners like the RS10 so that they can capture the tree width as it changes from the ground to the top. In New Zealand, we had a bit of a change in legislation around carbon credit calculations, and a lot of those are based off pine trees. But in New Zealand, we have a lot of native trees that aren't quite as straight, perhaps as the ones that are shown here. So being able to capture them with a SLAM sensor means you can get a lot more information. And obviously these are moving quite a lot. So the fact that you're getting clear views of the trees as you're going through is really testament to how good those calculations have become in these sensors. So this is just a top through for a forest environment, and you can see all the isolated trees there. This is an example from Wellington where a client had a scanner and they did a 30-minute walk with the sensor and got very good data with all the positions and shapes of all of the columns throughout the stadium. And then this is another one from Auckland Museum. And you can see that it's got some very nice clarity and kind of definition around those features. So for the RS10, there's an optimization which thins the data out. Natively with the 16-line LiDAR, the thickness of that noise is going to be about 2 centimeters. And then with the 32-line version, it's about 1 centimeter. But then it optimizes it down to 5 millimeters in the post-processing. With the kind of native noise with these SLAM sensors, unfortunately, that is unavoidable because it's trying to capture information whilst you were moving around. So this is the data we got from Whanganui in a top view. So we've got the point cloud overlaid there with those kind of 3 key items of interest over that contour map of the seabed. So we can see up the top is the wharf. Then we've got in the middle the sandbank. We didn't go through the whole thing, so just got the sides of it. And then to the left is the shipwreck. So for wharf inspections, going around with handheld scanners is quite a quick way to get some information underneath the wharf. You also get a load of pictures with these point clouds, so you can go through and see what the condition of the wharf structure is like. And then you can get information like the sandbank, so you can see kind of the tires and the edge of the sandbank there. And then this is a view of that shipwreck on the side of the sandbank. So Mark was taking the RS10 and holding it out over the side of a boat and capturing all of this information from there. So this brings us on to the final part of the webinar, the 3DR software processing. So how was this information processed and what was delivered? This is the final deliverable. It was a 2D PDF of the waterbed with some contour lines at half-meter intervals. All the data was provided in terms of the chart datum. So to get to this point, I was given a CSV file for the sonar data, and you can see all the XYZ points there. And then there is a .las file for all of the RS10 point cloud data that was collected. Both of these data sets are in the Whanganui local circuit, so they sit together straight away when you're in 3DR. So you can see the point cloud and the sonar combined here. And if we go and have a closer look, you can kind of zoom in and see all the individual points from the sonar in purple. If you measure between the 2 lines of the sonar at the bottom, it's about 10 meters apart. But if you go up towards the top, closer to the shore, it's about 5 meters apart. So the depth of the water does make a difference to those distances. I also got a lens aerial image to put in the background for the dataset, and it makes everything look a lot better. I did have to manipulate this a little bit though. The TIFF image that I imported from lens obviously has a height of 0. So I had to go into the coordinate system tab and change the height. The easiest way to do this, I find, is through free move, but there are a few options in there to get this to work for you. So then the first step in this process is the mesh creation. So if you go to the surface modeling tab in 3D mesh, there's quite a few different options. Meshing in 2 steps is probably the most suitable here, because you can create a dumb mesh and then you can go through and refine it. So for this first part, the average distance between points has been set at 7 meters. And you can see there's quite a few holes because when we were measuring it before, there's obviously like some areas where that data is further apart than 7 meters. If you go for 9 meters, I find that does provide better coverage, kind of enclosing that a bit more. But there are still some holes, especially down the bottom there on the right. So now we need to go to like a hole detection workflow. This is automatically set to be 3 times the average distance. But the other 2 options are to do an external border or a watertight mesh. So if you try to keep the external border only, it will fill all holes except the largest. And if you go for watertight, then it will try and create complete coverage across the entire site. So this is the external border, some nice coverage, and then watertight, it's completely closed it. So external border is definitely the way to go for this one. And then that brings us on to the next step of the workflow, which is the refinement of the mesh. So if you do the refined mesh from cloud, it's going to follow it very closely. And you can see that here where it's created quite a lot of noise and tension across the mesh. And I suppose that's just the nature of the data. It's not going to be like the same as a static laser scanner. So if you go for the second step, doing interpolation instead, you get a much smoother result over those changes in height on the waterbed. You can also fiddle the deviation error a little bit if you want. The closer that deviation error is to 0, the less it's removing noise from the data. So this is just quite a good overview of the difference there. So you can see the diagram there is showing how when you're doing refining from a cloud, you get a much more representative example of what is actually there in the data. So if you don't have very noisy data, this can be quite good. But if it is quite noisy, then it will follow it quite closely, and you'll end up with lots of rifts in the data. Whereas with the interpolation, it's kind of going through the average middle point there, creating points. So the next step in the workflow is a long direction. So this is great if you want to do any depths of object investigation. So I've got it set along the z-axis, and you can see it's shown instantly quite a difference across the surface there. So there's a few different ways you can represent this in terms of the colorization. It's showing that it's going from minus 5.64 up to 1.9 now. The default before had a few points that were like 0% of points, so quite easy to change. And then there's all these different options here that you can go through in terms of colorizing. The list of values is the best to create that more continuous heat map, so that's what I'll keep it with here. So the next part of the process is generating the contour lines. So just going to the mesh, having a little look at it here. It's a very automated process. So we just go to the contour lines under the extract tab. I want a step of 0.5 meter. So I'm going to set that. I want to have a major contour every 2, so every meter. And I end up with a map which looks like this. So you can export that straight to DXF in the command, or just create the view here. I want to put it on a PDF, so I'm going to create my views within 3DR itself. I'm also just doing a little bit of manipulation on the heights of the contour lines there, so they're a bit more visible when I do my PDF printing. The other data set that's really good here for getting more information on the heights on the waterbed is doing a gridded inspection. So you can set the steps for this. The default is 1 meter, and that's very dense data. It will probably crash your CAD if you have a large area like this. But spreading it out a little bit further, maybe every 5 meters, is probably a good spacing to go through. Obviously, it just depends on what output you need and what density you require. So this creates a pretty great view with all of those 5 meter spacings of all those changes in heights. Another deliverable that's pretty great here is slope analysis. So I'm just doing a default that's come in here of 5%, but instantly with that, you can see that it's shown the 2 kind of main channel areas there in the data, and there's a grid underneath. So pretty easy to do. And if you have a specific slope that you're looking for, then you can set that in the command as well. So this brings us on to the final step in the process, which is PDF report creation. So you just need to go to the View tab and save a view. So I'm just naming it here, Outputs Contour. And then under the report tab, you can just create a new chapter. This is the default 2D PDF report option. And from that, you can just drag and drop in your views to create these nice PDFs that you can just export straight from the command. A lot of functions within 3DR do have default outputs where it's already preloaded into the presentation, into the report tab for you. So I suppose that's it for kind of the main deliverables you can get out here. The key thing we actually wanted for this project was just the contour lines, but a height map would have probably been quite useful as well. We then also have the point cloud combined in here with all of the data. So this is just a little fly through that was generated. So obviously the point cloud data is already sitting in the right place relative to it. So you can use that to kind of go and have a look around. If you wanted to pull polylines out of the point cloud, then you could just go into the virtual surveyor tool and extract that information from the data as well. Yeah, the world's really your oyster. So that's been our webinar on combining the underwater data and processing it through 3DR. So we've done a bit of a background of the capture, gone through the field capture workflows and the 3DR software workflow. Do we have any questions? Don't forget to put them in the tab. So we've just got a few questions coming in. Oh, sorry, make sure my screen is visible. So for the first question that I've got, can you combine other point cloud types, not just MLS? Yeah, you absolutely can. The key thing is that you have some real world coordinates in there to make that as easy as possible, or some form of target so that you can have a connection between the data sets. Yeah. The next question I have is, what is involved in the data processing before 3DR? So this one is, I think, referring to both the file that was created for the CSV of heights from the sonar and for the point cloud. So I'll get you to answer the question about creating the CSV in a moment, Mark. But in terms of the actual point cloud from the RS10, you would want to have, you'd take it into a software called Copri. It's for SLAM data. It's pretty like, it does most of it for you. So you basically just have to optimize the data. So for this data set that Mark captured, we had multiple individual walks. So I took them into Copri and I basically just applied the Rhinex data and then went through a 4-step process. And I think it took about an hour to process, but that was mostly just it going through after I clicked the start button, rather than me actively like registering all of the data together. So it's a pretty, I suppose, grunty process that just kind of runs in the background rather than being as actively involved.
Okay, and to answer Jason's question, the MLS data was really just for visualization for ourselves. The client had no real interest in that. They were just after the sounder information. But it was a very good exercise for us. And Caleb, in terms of comments about Maritime New Zealand requirements for USVs, essentially these fit into the same sort of category or a similar sort of category as UAVs, and there are requirements for commercial applications that everybody needs to adhere to and apply to Maritime New Zealand for approval for use in public navigable waters. So there is not a great deal of documentation from them at this stage, but hopefully that will improve in the future.
So can you adjust the number of decimal places when doing grid values? So this is from Rodney for the 3DR grid of points. That's a great question. Unfortunately, I am not sure on the exact answer for that, so I will have to find out and get back to you on that one. I've never tried before. So I think that's the last of the questions now, unless we have any more coming in. Okay. Well, thank you everyone for attending to our first webinar of 2025. On the screen here, you can see a little QR code. This is for last year. We sent out a feedback survey and we'd really appreciate it if you guys could give us some feedback on your favorite webinars from last year and what you want to see more of this year. Thank you so much for your time.